This lecture will focus on laterally unsupported beam. The design strength of laterally unsupported beam will be calculated based on the codal provisions which is given in clause 8.2.2 of IS 800/2007. Now, in case of laterally unsupported beam, the lateral torsional buckling will play an important role, and because of lateral torsional buckling, the full plasticity of the section will not be developed. That means, the member will fail before attaining its full bending stress of the section. It will fail due to lateral torsional buckling, and this lateral torsional buckling happens in case of steel rolled section. Unlike RCC section or the stocky section, their lateral torsional buckling does not come into picture, but in case of such type of section where we have made economic of the in terms of the material, we face this type of lateral torsional buckling, and if we do not provide support laterally, then such type of buckling will come into picture. So, this buckling comes because of the cross sectional shape, then support conditions and the length, effective length. So, what is the effective length, what is the support conditions and what is the type shape, depending on that the lateral buckling moment will be calculated, and because of that how it is going to fail, that will means how we are going to calculate the lateral buckling strength, and then how we are finally going to find out the design bending strength of the section when the section is laterally unsupported will be discussed. So, if we see the design bending strength, which we can write as MD is equal to beta B ZP into MD is equal to beta B ZP into FBD. So, the design bending strength of laterally unsupported beam can be written as ZP into FBD into beta B, where beta B we can consider as 1.0 for compact and plastic section, and we can consider as ZD by ZP for semi compact section. So, depending of the type of section, the beta B value will be calculated either 1 for compact or plastic section, or the ratio of ZD by ZP for semi compact section. And this ZP is basically the plastic section modulus of the cross section, and FBD is the design bending compressive stress. So, design bending compressive stress FBD we can find out from this formula, XLT into Fy by gamma m0. This is the bending stress reduction factor to account for lateral torsional buckling. So, the design bending compressive stress FBD can be found from this XLT into Fy by gamma m0, where XLT is the bending stress reduction factor. So, what is the bending stress reduction factor, that we need to calculate. This has been calculated as 1 by phi LT plus root over phi LT square minus lambda LT square, and in any case it should be less than or equal to 1. So, the reduction factor XLT we can calculate from this expression, where the phi LT value can be calculated as this, that is 0.5 into 1 plus alpha LT into lambda LT minus 0.2 plus lambda LT square, right. So, phi LT value can be calculated from this expression, and where we can see that there is a term which is alpha LT and also lambda LT, that non-dimensional slenderness ratio, that we have to find out. So, if we know the value of alpha LT, and lambda LT, then we can find out phi LT, and if we know phi LT, then we can find out the value of reduction factor, that is XLT. So, bending compressive stress reduction factor XLT can be found from this. Now, what is alpha LT? Alpha LT is the imperfection factor for lateral torsion. So, alpha LT is the imperfection factor for lateral torsional buckling of beam. We can consider this as 0.21 for steel rolled section. Okay. So, for all rolled section, the value of alpha LT can be found as 0.21 and it will be 0.49 for welded section. That means, if we suppose use a plate to make a I section with the use of welded, say with welding we can make a I section from a plate, then for such type of section we can use alpha LT as 0.49. Otherwise, for the rolled section we can use alpha LT as 0.21, and lambda LT is, I have told that is non-dimensional slenderness ratio lambda LT. So, this can be calculated from this, that is beta B ZP Fy by MCR, right, beta B into ZP Fy by MCR, and it has to be less than or equal to, in any case, 1.2 ZD Fy by MCR, right. So, we will calculate the non-dimensional slenderness ratio from this expression, which is beta B ZP Fy by MCR, and this lambda LT value should be less than or equal to this, that is root over 1.2 into ZT Fy by MCR. So, this lambda LT also we can write as Fy by FCRB, where FCRB is the MCR by beta B ZP, right. So, lambda LT we can find from this, right. Now, what is MCR? MCR is basically the elastic lateral buckling moment. This is given in clause 8.2.2.1 of IS 800 2007. We can find out the elastic lateral buckling moment MCR, and a formula has been given for calculating the value of MCR, that is as pi square E I y by L T square into G I T plus pi square E I W by L T square, right. So, the elastic lateral buckling moment can be found from this expression. This can be written as beta B ZP into FCRB, right, where here the different variables are given, which we can find out from clause 8.2.2.1. the parameters like I T is the torsional constant. So, I T will be for open section, it will be B I T I cube by 3. So, how to calculate I T, that through one workout example we will discuss details. Then I W is the warping constant, I W which is warping constant, I Y is the moment of inertia about weaker axis. Similarly, R y is the radius of gyration about weaker axis. Then H f is the center to center distance between flanges. That means, H f will be, say, if I consider an I section, then the HF value will be center to center distance of the flanges. This will be HF, and G will be the shear modulus, and LLT will be the effective length for lateral torsional buckling, which is given in clause 8.3, right. So, effective length for lateral torsional buckling LLT can be found in clause 8.3, and FCRB is the extreme fiber bending compressive stress. FCRB is the extreme fiber bending compressive stress corresponding to elastic lateral buckling moment, and this FCRB can be expressed as like this: 1.1 pi square E by LLT by RY whole square into 1 plus 1 by 20 LLT by RY by HF by TF whole square, right. So, FCRB, the extreme fiber bending compressive stress corresponding to elastic lateral buckling moment, can be expressed from this. Okay. This is also given in the code, where the details can be found, and also we can find out this value, the FCRB value, from table 14. Instead of calculating all this, we can find out the value from table 14 of IS 800/2007 with respect to KL by RY and HF by TF. So, for different value of HF by TF and KL by RY, we can find out the value of FCRB in table 14. That means, in place of calculating through this expression, directly we can find out the value of FCRB from table 14, and the FBD value can also be found directly from table 13. Corresponding to different FCRB value and FY value. For different FCRB and FY value, we can find out the value of FBD. FBD, the design compressive bending stress, right. So, what we can do means, without calculating through expression, directly what we can do, first we can find out what is the KL by RY ratio, what is the HF by TF, and from that we can use table 14, and using table 14 we can find out the value of FCRB, and once the FCRB value is obtained, then corresponds to FCRB value and FY, we can find out the value of FBD. So, directly I can find out the design compressive bending stress, and then I can find out the design bending strength of the member. Now, also we can find out the MCR value in a simplified manner from this formula, that is pi square EIY HF by 2 LT square into 1 plus 1 by 20 LLT by RY HF by TF whole square, right. This is the simplified equation which may be used in case of prismatic members made of standard rolled section, rolled I section and welded doubly symmetric I section. So, to calculate the elastic lateral buckling moment MCR, we can use this simplified formula in case of prismatic members made of standard rolled I sections and welded sections. However, the MCR for different beam sections, considering loading, support condition and non-symmetric section, we can find out more accurately using the method given in annexure E of IS 800/2007. So, in annexure E, the details are given, and more accurately we can find out the value of MCR through annexure E. So, the things whatever we have discussed, I am just quickly going through this PowerPoint. That is, first we can find out design strength. So, the design strength for lateral torsional buckling has been calculated as per the codal provisions, and I am very quickly going through those formula which I have written in hand. So, we can see that first we have to find out the design bending strength for laterally unsupported beam from this formula, that is M d is equal to beta b z p f b d. Now, this f b d we can find out from this design bending compressive stress, that is x L t into f y by gamma m 0. Now, again I am repeating that this design bending compressive stress is reduced by this factor x L t. This x L t is called bending reduction factor, bending stress reduction factor, to account for lateral torsional buckling. So, if lateral torsional buckling is present, then this factor has to be multiplied to find out the design bending stress, right. So, our main job is to find out the x L t value. Now, this x L t value can be found from this expression, right, where phi L t can be found from this expression and alpha L t can be considered as 0.21 or 0.49. Then lambda L t, the non dimensional synchronous ratio, we can find out from this, right. So, the non dimensional synchronous ratio can be found from this expression. So, if we find the lambda L t value and if we know the alpha L t, then we can find out the value of phi L t, but to find lambda L t we need to know M C R value. So, our next step is to find out the value of M C R, which is given through this expression M C R. This is available in the code in clause 8.2.2.1, the details are given. So, from that the value of M C R can be found. Now, where here the different parameters are defined, like I t, the torsional constant, are defined as summation b I t a cube by 3, and I w is the warping constant, I y is the moment of inertia about weaker section, r y is the radius of gyration about weaker section, L L t is the effective length for lateral torsional buckling, and H f is the center to center distance between flanges, T f is the thickness, and G is the shear modulus. So, from these parameters I can find out the value of M C R, and needless to mention here that this elastic critical buckling moment depends on the few factors, like one is L L t, that is effective length of lateral torsional buckling, then the shape of the section, for which the I y value and other values will be dependent, right. So, depending on those factors, finally, we can find out the value of M C R. Okay. Also, we can find out the F C R B value, which is the extreme fiber bending compressive stress corresponding to that elastic lateral buckling moment. So, F C R B value also we can find out from this expression, that is 1.1 pi square E by L L t by R y whole square into root over 1 plus 1 by 20 into L L t by R y by H f by T f whole square. So, F C R B value can be found from this expression. Otherwise, very quickly we can find out the F B D value from table. The code has made us easy to find out the value of F B D without calculating through those expressions which are given. So, what we can do? We can find out the value of K L by R y and H f by T f. So, once we find the K L by R y and H f by T f, we can find out the value of F C R B, which is given in table 14. So, in table 14 corresponding to this value, we can find out the extreme fiber bending compressive stress FCRB. So, once we find FCRB value, then corresponding to that FCRB and Fy, we can find out the design compressive bending stress. So, design bending compressive stress FBD can be found from this FB from table 13 or 13b, depending on the type of means section. Okay. So, the FBD value once we get, we can find out the value of MD. So, this is how we can find out the section bending moment. So, in today's lecture what we can see that due to unsupported length of the member, laterally unsupported length of the member, there is a chance of lateral torsional buckling. If the member, the cross section is not stocky in nature, then lateral torsional buckling may play an important role. And because of lateral torsional buckling, before developing the full bending stress, the member may fail, and therefore, we have to find out what is the lateral torsional buckling moment. So, what we have done? We have calculated the lateral torsional buckling moment, then we have found the extreme bending stress due to this lateral torsional buckling moment FCRB, and then we can find out the FBD. So, FBD, the design compressive bending stress, is nothing but Fy by gamma m0 into some reduction factor which is called XLT. So, because of the presence of lateral torsional buckling of the section, the reduction factor has to be calculated, which is called XLT, and once reduction factor is calculated, then we can find out the design bending stress, design bending compressive stress, and then from that we can find out the design bending moment, the design bending strength of the section, which is laterally unsupported, can be found in this way. So, in next lecture we will go through one example, then the detail of the things will be clear. Thank you.